time research is to understand something called thermalization, which is like how, in a very simple terms, how can we understand temperature at the quantum level? Yes.
How do you measure these systems, but any kind of measurement interferes with the system and thus could add more energy into the system? So how do you measure these super cool systems?
Okay, once we measure it, we know we destroyed the system. So we kind of, so the thing is, we need to know, so it's like multiple stages, right? And you need to know once, okay, so after the Zeeman's law, it goes to the magneto-optical trap, or the MOT, okay? And after that, it's going to go through the subdoppler cooling and all that. But before it goes to the subdoppler cooling, I need to know what I started with. So you do all these measurements to characterize this stage, and then you go on to the next one, and then you go on to the next one. And once we take measurements at the very end of the real experiments, that's when we take data to actually learn something.
Oh, so in order to create a video, so to speak, you have to say, take 100 frames. You have to recreate the experiment 100 times?
Yes. But like this thing that you saw like takes like 2 seconds to create.
Oh.
So you just like click a button on the computer and it keeps running. That's how cool it is. Yeah.
Are there only certain atoms that you said like sub 20 nanokelvin? Like, is there a certain class of
Okay,
atoms?
actually, I don't know, but what I know is that these type of atoms are the alkali atoms.
Okay.
Okay, so usually we work with that.
Okay.
Yes.
Why is the process for cooling so complicated?
Okay, explain complicated.
Because you couldn't even explain it to us. That's why I think.
Oh, subdoppler cooling. Okay.
Subdoppler cooling.
Okay, because it's until now I just used the high school physics type of thing, and it's enough to explain these kind of things. But if I wanted to explain subdoppler cooling, then I have to explain to you that these energy levels, like these two tiny ones, are actually made of other energy levels, and these tiny energy levels, each one changes in a different way with the magnetic field. And to actually be able to do this kind of cooling, you have to create some kind of something called Sisyphus cooling, according to the poor guy, which is pushing the rock all the time, like all the way. And it's a standing wave type of thing where a particle has a kinetic energy, okay? Then it reaches to the top, it loses all the kinetic energy, and then you make it go to a different state. And then it goes up again, different state. And that's how you lose more energy. It's more complicated because I have to explain the substructure of the energy levels.
So the way that you're cooling it is that you're making sure the atoms are falling to lower energy levels.
It
And
goes
then-
to the upper one, and
And
then
then
you get it up.
of course, and then but that's the process of the cooling.
In a way, yes. Any other questions?
Time for one more.
Yes.
What's up with the blue mont?
Ah, yeah.
Huh?
So it's something that actually people achieved. And I remember my supervisor, whenever he talked to any of these people, oh, so do you actually understand this thing? And he says, no, but it works. And our job, or what we are trying to do is actually try to understand this much better in hope of 2 goals. One goal is that we are what I showed you here is cesium. We're also working on lithium. And once we make this process work, maybe it will be very beneficial for lithium over other kind of cooling techniques. But a more like ambitious goal is maybe if we made this a standard thing, maybe the other atomic physics labs in the world can actually use it. Yes.
Can I ask another question?
Go for it.
When you said that, so this is a step in the process, and you're essentially and you can correct me if I'm wrong, but you're refining the process and able to go to another step, which is to use these ultra cooled atoms to simulate, for example, real world phenomena,
Yes.
and then utilize that in some sense. How exactly are you utilizing super cooled atoms to simulate like real world phenomena? For example, like you mentioned, the black hole. I can't remember exactly what it was.
Okay, the black hole is actually a cool example. So when you achieve a BEC, okay, the BEC, it's physics, the equations themselves can map in a very nice direct, I don't know if it's direct, because I'm not an expert, but it can map to that of general relativity equations. Okay, so for example, I'll give you an example. If think of it as a ball of gas, as we did before. Okay, and you have the control over the density. Like I can choose this part, I want it more dense than this part, make it less. You can engineer it, okay? And the interesting thing is, as in the space-time in the universe itself outside, light is the thing that actually travels. These VECs, sound waves, is the thing that travels. And the sound wave, its speed depends on the density, right? The more dense, it will be faster and so forth. So if I was able to engineer these kind of things and the physics is the same, then I can make how the light travels in the space-time can actually match how the sound waves travel in the Bose-Einstein condensate or the ball of gas. Does that explain it?
Yeah, yeah, that's fair.
Any other questions?
Well, Jazakallah khair. So much. That's the end of our talks today. Ended off with a banger, not to say everybody else's presentations weren't also amazing. Yeah, so I'll throw this back up again if anybody's interested. And if you like not just this style, but also a back and forth dialogue, we highly encourage everybody apply to our Majlis event. If you don't sign up now, it'll be on our Instagram, inshallah. Okay, we're all done. Jazakumullah khair. Thank you so much. So we have to clean up. I'm going to ask everybody for a favor. It usually takes us maybe 25 minutes. It might take us 5 if we all work together.